Okay, so now let us discuss a problem and see, get a more in-depth insight of how this Monte Carlo simulation technique works. So for this, I'm going to take up a problem which is given in my Ranganathan textbook, example 7.6. So this one is actually example 7.6. So if you have the book, I request you to refer to it. So now what I'm going to basically do is I'm going to explain to you each and every step of this problem, and certain steps which may have been missed in that example, so that we can get a greater insight and understand the problem properly. So the problem given is the strength of the strength of an actually loaded short column is given by R equals 0.67 C AC plus AS times F. So be careful if you're seeing the book. This term is actually not printed in the book, so this is the equation plus AS times F. Okay, where what do we have? The cube C is the cube strength of the concrete. F is the yield strength of the reinforcing bars. Right. AC. Here I have AC right here in this equation. I have AC. So AC is the area of the concrete. AS is the area of the steel. So AS is the area of the steel. Now the size of the column is given as 250 mm by 500 mm. 250 mm by 500 mm. And mu C. What is mu C? The mean. The mean cube strength. The mean cube strength is given as 19.54 megapascal. Sigma C, which is my standard deviation of my cube strength, is 4.1 MPa. Mu F is my mean yield strength of the steel, because here if you go back, F is the yield strength of the reinforcing bars, right? So mu F is my mean yield strength. Sigma F would be my standard deviation, 46.9 MPa, and AS given is the area of the steel, 1250 MPa. So what is the problem? C and F are normally distributed. Okay, determine distribution of R using the Monte Carlo simulation. So this is the problem that we are going to deal with. We are going to determine the distribution of R using my Monte Carlo simulation technique. Okay, so let's see how to approach it. And since it's a computer simulation, from an examination point of view, we will not get any results. We can just write down the steps and mention how this is calculated. But since it's a simulation which involves 1500, 1500, 2000, depends on you. There's many simulation values. You cannot possibly predict what your result is going to be. But what is more important is you need to write down the steps that are involved very clearly, so that using those steps, if anybody is going to carry out a computer simulation, they can easily carry it out. So let's move and see how can we now solve this problem. Okay. Yeah. So first things first is my area of let me go write down the resistance equation once again. R equals to 0.67 times C AC plus F times AS, right? That is what it is. So I know, what do I know? I know mu C is known to me, then sigma C is known to me, mu F is known to me, sigma F is known to me, AS is known to me. It's 1250 is given to me, 1250, okay, mm square. And I know the area of the column. The cross-sectional area of the column is known to me. I need AC. So AC would be, the cross-sectional area of the column is given as 250 mm by 500 mm minus the area of the steel, 1250 mm squared. Okay. So what do I get? So then just pause and calculate, because I already have the value, so I'm just going to copy it. 123750 mm square. So this is the area of the concrete that I have. So now I'll plug this value back into my equation. So the resistance becomes 0.67 times 123750 times C, the cube strength of concrete, plus 1250 times F, the yield strength of steel. So what do I get? Finally 8291.2.5 times C plus 1250 times F. So this is my equation for the resistance. That is clear. Okay. Now what do I have? So this resistance for the equation, if we try to compare with the previous videos, I had mentioned that the resistance of the equation, so the resistance equation depends on many factors, x1, x2, dot 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 xn. So here I actually have two factors here, x1 and x2, which is the cube strength of concrete and the yield strength of steel. Okay. Now you're getting a hold of it. So these are going to be your variates, where we are going to vary these values. We are going to vary these values. We are going to using a variation of these values will generate R values. Okay. So this is my variate. So what can I write? Let me see. So Fy, my cumulative probability of C, Fy, okay, cumulative probability of C is my psi that we have discussed before. From the table we can find out the cumulative probability of any point, right? Psi of C is my cube strength minus mu of C divided by sigma of C. This would be my variate, the deviate, the random deviate for C, right? Random deviate for C. Okay, random deviate for C. So this is going to be my random deviate for C. Okay. Now I know here mu values. Okay. So so psi of C minus mu C value is 19.54 divided by sigma C is 4.1. Sigma C is 4.1. Okay, this one is going to give me my mu C. So now what do I have? I can do the inverse of this one. So C would be what? C minus 19.54 divided by 4.1 is going to be psi inverse of mu C, correct? Psi inverse of mu C, or what can I write here? C is 4.1 times psi inverse of mu C plus 19.54, right? So I can write this plus 19.54, psi inverse of mu C plus 19.54. So now this mu C is going to vary from 0 to 1. Once we are going to vary from 0 to 1, we can find out psi inverse from our tables for various values, or even from using our calculators we can find out psi inverse from 0 to 1 when it varies, and depending on that we are going to generate C values. So now you see I'm going to vary mu C from 0 to 1, and with this variation I'm going to get a variation of the C values, right? Now the same thing will also happen for the second variate. Here is F. Okay, so F is also going to be what? Okay, written here. Yeah, so F is also going to be what? F is also going to be something similar, where we have here my sigma F. Sigma F is 46.9. Psi inverse, the inverse cumulative of nu of F, okay, plus my mu, the mean value. So this is my standard deviation that we have discussed here. I think it's given in my here, yeah, mu F and sigma F. So the f value is going to be something like this. So similarly we are going to vary this from 0 to 1, and we are going to generate enough f number of values, enough number of values for f. Okay, so now if I go back to my equation here, so I can generate various values of c using my new. Okay, and by varying my new c I can get various c values, and by varying my new f I can get various f values. With that, if I add them up, I can get my resistance value. So there can be actually infinite number of possibilities where you can have the resistance values. We can how you can generate the resistance values. The infinite number of resistance values can be generated with that. So now what do I have here is, so once you will carry out the simulations, you don't know, because if you're from an examination point of view, you are not going to carry out computer simulations, right? So you have no idea what is going to be the results. So we have to just leave it here, saying that using these formulas we are going to calculate the values of R. But this values of R that we are going to generate, can we check them? Like, can we give them a guideline that this needs to be checked? Yes, we can do that, because if we have sufficient number of R generated, R which is a function of my C and F, if I'm varying this C from 0 to 1 and F also, sorry, from 0 to 1 and F also from 0 to 1, you can have actually infinite number of combinations. After an infinite number of combinations, you have a big set where you have values of R, R1, R2, something like that. You have a big value of R, and can be anything. It's depends on number of data points you are trying to assume. The more the number of data points you are going to assume, definitely the more will be the accuracy. Now, using this, you can actually make a distribution of R, something like this. Okay, you can actually make out a distribution of R, and with that you can find out mu R, the mean of R, and you can also find out sigma R, the standard deviation. So this is mu R and this is the sigma R. So this is sigma R, and you can find out mu R and sigma R. Now, how to check whether these mu R's you have found out are precise and accurate? Okay, so what I found previously was that R equals 82912.5 times C plus 1250 times F, which means that mu R is going to be 82912.5 times mu C plus 1250 times mu F. So now you're going to run your simulation. Okay, so maybe do for 100 calculations, and you find out that you calculate the mean, the standard deviation. Let's first see the mean. You have to find out the mean. You know the mu C, the mean is already given to you. You know the mu F. You put it there, and you see that this mu R value that you are getting from carrying out your simulation, is it closer to this value or not? Okay, so and this is for mu C, you can check, and that, for mu R you can check, and similarly for sigma R also you can check. How can we check? Sigma R is going to be 82912.5 sigma C whole square plus 1250 sigma F whole square, a root under of this, or I can say sigma R square is equals to this, right? You already know these formulas. So after running n number of simulations, this can be 500, 1000, 10,000, depends on you, your computational capabilities and your requirement. You can actually find out the mu R and the sigma R values from your computation, not from here. Okay, from your computation you find out, and theoretically this your value should be this. So your mu R from your computation or your simulation, let's say mu R from your simulation, needs to be very, very close to this mu R that I have calculated. The mu R is here, needs to be very, very close to this value. Similarly, sigma R from my simulation needs to be very, very close to this sigma r, this one that I have calculated here. Okay. So from an exam point of view, it's not possible for you to carry out the simulation. So at least what you have to mention clearly is all the steps involved, and it's basically like you're giving a guideline to somebody who is going to, carry out this Monte Carlo simulation technique. So here I would end my lecture, and then I think your little bit idea you have gained about this simulation technique. For more information, I recommend that you go through the Ranganathan textbook, and you will get a better idea of the technique itself. So thank you.